All right. Good morning, everybody. Let's continue from where we stopped. As you remember, we were talking about inverse transforms and transforms of derivatives. So that is what we did last time in the last 15 minutes, right? The first translation theorem, translating the function of this f, right? That's a Laplace transform a units to the right, or just shifting a units to the right. That means that if you multiply this f function, f of t, by e to the power at, right? So it is Laplace transform will be capital F of just s minus a. And we have already proved here that theorem, that's a proof. And with this example, here we have using the first translation theorem, evaluate Laplace transform of e to the power 5t, and that is t cubed, right? So first we have to here identify that this t cubed, that is our f function, f of t is equal to t cubed, right? And we know the Laplace transform of this function is, what is it? That is 3 factorial something over s to the power 4, right? And because of this 5, then we need to substitute instead of s minus 5. And actually we got this solution, right? That is 3 factorial s to the power 4. That is our f of s. Now after that, instead of f of s, right, because of this e to the power 5t, the theorem says that we don't have to evaluate this again using the formula. Just this function f of t, evaluate it as Laplace transform, and after the substitute this s minus a. Here our a is 5, right, for s in this function. That's why Laplace transform of this function is 6. Here we have 3 factorial, that's equal to 6 over s minus 5 to the power 4, right? How about b? And also we did this the last time. Just if we recap this, as here, if you identify first a, what is a here? That our a is negative 2. And our function f of t here is f of t equals cosine of 4t, right? So now if you just evaluate Laplace transform of this cosine of 4t, right? As cosine of 4t, that's equal to s over s squared plus 4 squared, right? Now because of this thing, then that will be equal to the f of s. Instead of s, if you substitute s plus 2, right? Because a equals negative 2, right? S minus a, that is s minus minus 2, that's equal to s plus 2 over s plus 2 squared plus 16. Okay. Inverse form. By a similar way, we can find the inverse of this function, f of s minus a. Okay, what is it? First, this f of s minus a, right? It is actually, I can just write this f of s minus a as this function f of s, where this s should be substituted by s minus a. These two things are exactly the same thing. It's just writing this function in different form, right? So now we know the Laplace transform this thing, right? That is equal to f of s, that is f of t, and because of this thing here we have e to the power at, e to the power at times f of t, right? So we know the Laplace transform of this function, that exponential function here, e to the power at times f of t, that is equal to capital F of s minus a. Okay, regarding this, let's see another example, partial fractions. Repeated linear factors. So evaluate this inverse Laplace transforms of these two functions. Here our f of s is given. This is the first example. That's the second example. First parts actually I'm just going to do, without writing this, I have already prepared earlier so that we can save more time. Otherwise it's taking a lot of time, as you know, just elementary calculations. So here a, that is our f of s, right? F of s equals to s plus 5 over s minus 3 squared. As we know that actually when we are dealing with this kind of problem, we have to decompose this fraction, right? That is an algebraic fraction or just rational function. We have to decompose this. So when we have repeated factor, in this way we can decompose this. That is a over s minus 3 plus s minus 3 squared. And here we have a plus b. And you know how to determine this capital A and capital B, right? Here we have If you just cross multiply here, bring into the common denominator, s minus 3 squared is a common denominator, multiply numerator and denominator by s minus 3. So I will have here a times s minus 3 plus here we have b. So if s equals 3, for example, I get b, right? If s equals 3, this thing is equal to 0. 2 times 3 is 6 plus 5 is 11, so b equals 11. Now let's say s equals 4, for example. It's easy to calculate, right? There's one purpose. Actually, I'm substituting this 4 for s. 4 minus 3 is equal to 1. A equals 11. Substitute here. I can get the value of a. A is equal to, what is it? 2. So that means that this fraction can be decomposed in this form, or we can express it as a partial fractions of these two fractions. So that is, here we have 2 over s minus 3, and b equals 11 over s minus 3 squared, right? Now, instead of this s minus 3, if I just write here capital S, here we have s squared, right? We know how to evaluate these things, right? Because we know that if you just evaluate Laplace transform of t to the power n, what is it? It's just equal to n factorial over, what is it? S to the power n plus 1. So here just a number, right? Here we have s to the power something. So I can just do this substitution here. So here we have, okay, we need to calculate the Laplace, inverse Laplace transform of this. So that's equal to this thing, right? So now what I did here is, okay, guys, here I took this to out, okay, because s, all right, because in this example here we have 2 s minus 3, right, and 11 over s minus 3 squared. So here we have 11, and here we have 1. Give me a second. Let me just correct this mistake immediately. Otherwise, it will be mess. It should be 1. Okay. Okay. So here, if I just take this to outright, here we have 1 over s minus 3. 11 is also constant. Here we have 1 over s minus 3. Oh, why? Okay. Right. So now, what we have to do here is, so we need to evaluate it is transform, right? Here, our f of s, that is equal to, or let me just write here, even without this, 1 is equal to 1 over s minus 3, right? It is the same thing as, what is it? I can just write it as 1 over s, where s should be replaced by s minus 3, right? These two expressions are exactly the same thing, just using different notations, right? So that means that evaluate this thing when s equals s minus 3, or just evaluate this thing. It's the same thing, right? And also this thing is 1 over s minus 3 squared, right? I can just write it as 1 over s squared, right? Where s should be replaced by s minus 3. Okay. So when it is so, what is the actually, what is it? Inverse of this thing. If you just evaluate here, inverse Laplace transform of 1 over s minus 3, right? And here I can write here inverse Laplace transform of 1 over s, where s should be replaced by s minus 3, right? So when it is 1 over s, we know it is, what is it? Inverse Laplace, right? That's equal to just 1, right? So here we have just 1, and because this s minus 3, here we have e to the power, here we have minus 3, right? It is 3t, right? And here I have 1. Okay. Now next thing is, here we have inverse Laplace transform of 1 over s minus 3 squared. right? Now also I can write it as inverse Laplace transform, right? I can just write it as 1 over s, where s should be replaced by s minus 3, right? Sorry, s squared, because here we have squared, right? And we should replace, if I just replace this s by s minus 3, we will get the same expression. Now we know what is this thing, right? S squared, here just 1. And what functions Laplace transform equals 1 over s squared? We know that that is just t. So here we have t. Now because of this, here we have e to the power 3t times, here we have t, right? Now if I substitute here, then we get this result. Laplace inverse Laplace transform of this 2s over s minus 3 squared is equal to, here I have 2, right? The first thing is 2 times e to the power 3, e to the power 3t, right? And plus, next thing is here we have 11, t times this, so 11 times t times e to the power 3t. Okay. All right. Another second example, question B. Here we have s squared, right? That is s squared. Not s squared. Here we have inverse Laplace transform of s over 2 plus 5 over s squared plus 4s plus 6. Now, first thing is, we know that this thing is f of s. So first we have to decompose this fraction, right? And that actually, in the first step, I can just write it as s plus 2 squared plus 2. Because here we have quadratic expression, I cannot factorize this. Why? Because discriminant is less than 0, right? We cannot factorize this. So the only way I can write here is, I'm just trying to write everything in terms of s plus 2 squared, because here is squared. How can I just take out something squared from here, right? Because we know that we are familiar with cosine and sine functions, inverses. One thing is that is like k over s squared plus k squared. Another one is s over s squared plus k squared, right? And it looks like something like this, right? If we have s something squared plus constant number squared. Okay, now in the next step, again, we have to decompose this. Before doing this, I'm just going to write this as the sum of these two fractions. The first one is s over 2 plus 5 over 3. If I just take this 1 over 2 here, s plus 2, 1 over 2 plus times 2 is 1, 1 plus 2 over 3, here we have 5 over 3. Right? Just doing some simple fundamental algebraic manipulation on this algebraic fraction. So now here we have a plus b over c, right? I can just write it as a over c plus b over c. So that this thing is, here we have 1 over 2 here, and here we have s plus 2. Denominator remains unchanged here, plus here we have 2 over, so just a constant number, 1 over s plus 2 squared plus 2, right? Now instead of this s plus 2, if I just write here capital S, what do we have here? Here we have s squared plus square root of 2 squared. And how about here? We have 1 over s squared plus square root of 2 squared, right? Actually, to write this in this form, here, square root of this number is missing here. I just multiply by square root of 2, square root of 2. So when we do so, then we will have here, all right, Laplace, inverse Laplace transform of this thing. And after that, we can just separate them. Here 1 over 2 is a constant, take this out, right? Inverse Laplace transform of this algebraic fraction, here we have this, and 2 over 3, 2 over 3, and here we have this thing, okay? And also one more thing, I am going to multiply this, for example, here, times square root of 2. And here we have times, maybe it's here, times square root of 2, right? And what is it? Here this 2 is square root of 2 squared, right? It looks like to this, right? Here we have k squared, right? And here, instead of this s plus, I can just write s, right? Here, if I just take this s plus 2 as s, for example, what I have here, s over s squared plus 2, right? And here we have k over k squared plus 2, right? Now what we have here then, dot, 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 the Laplace transform of this thing, the answer will be, let's say this answer is, what is it, our f function, some let's say g function. Okay, the g of t will be, here I have 1 over 2 times, because of this s plus 2, I have here e to the power minus 2t times, and instead of here we have now s over s squared plus 2, right? This one is square root of 2 squared. So here we have cosine of square root of 2t, right? Plus, how about here? I have 2 over 3 square root of 2 times, and here we have k squared, right? So because of this s plus 2, here we have e to the power minus 2t times sine of square root of 2t. Okay, that is how we use the translation about the s-axis. All right, next example, an initial value problem. That's the one problem related to this topic, okay, operational properties, that is translation about the s-axis. Now, I think, guys, I hope now you are already familiar with this. Now you get some idea about how we are actually using this Laplace concepts to solve differential equations. Now here we are given second order linear differential equations, right, with constant coefficients. So here we have the coefficient of y double prime is 1. Here we have -6 plus 9. And here we have t squared e to the power 3t. And also in different method, we can use the, solve this, because here we have just the product of polynomial function and exponential function, right? And now you will see that using Laplace transform is more practical and more, let's say, rigorous. And also in terms of saving time, it is really, really much better. So now immediately, what we have to do is we just take Laplace transform of both sides of the equation, right? And by using the linearity property of Laplace transform, I can just write this thing, because here we have alpha times something plus beta times something plus gamma times something, right? And we know that it has, or it holds, linearity property. So that is equal to Laplace transform of the first term, that is y double prime, minus 6 is constant. I can take this out now. Minus 6 Laplace transform of y prime plus 9 times Laplace transform of y. On the right hand side, we have Laplace transform of this function, right? So now, let me just evaluate the Laplace transform using the theorem. What we have here? Here we have, because the order is 2, so we start with s squared. S squared. So here we have capital Y of s minus, now here we have s, y of 0 minus y prime of 0. Okay, we are done with this. Minus 6. How about here? Here y prime, right? So we start with s times capital Y of s minus y of 0, because it is decreasing, right? The power of this s is decreasing. Anyway, plus, how about this? Take this 9 out, and Laplace transform of y is equal to capital Y of s. And on the right hand side, now we are familiar with this. What we have here is, here I have something like this, e to the power 80 times f of t, right? So what is it? It is just equal to, first I need to evaluate this and change the s with s minus a. Here our a is 3. So that is equal to Laplace transform t squared is 2 over s cubed, right? Because it is multiplied by e to the power 80. So instead of s, I write here s minus 3 cubed. Okay. So next step is, what we have to do is we need to substitute the given values. As you see here, initial conditions are given here. Y of 0 equals 2. So y of 0 equals 2. And y prime of 0 is 17. This thing is equals 17. And also this one is 2, right? And that's all. Now y of s is a common factor. Just take this out. Now we have this expression. So here we have s squared, minus here we have 2s, right? And here we have minus 6 times minus 12. And just simplify this. Here we have minus 6s plus 9. Y of s. On the right hand side, And also evaluating some other things here. We have 2s plus 5. We are just taking this to the right hand side. And on the right hand side, we have also this algebraic fraction, right? And divide both sides by this. It's just solving like linear equation. If you divide both sides by, as you see here, this thing is a perfect square, right? That is s minus 3 squared. And dividing both sides by this, so this will come here, s minus 3 squared, and here we have s minus 3 to the power 5. That is 2s plus 5 over s minus 3 squared plus 2 over s minus 3 to the power 5. Actually, this form is really good, right? And also we can just write this separately, this 2s plus 5. And here we have repeated root again. So you know how to do that. I can just write it as a over s minus 3 plus b over s minus 3 squared, right? And actually forming our identity, we can determine the value of a and value of b. So we can just find that it's equal to 2, this is equal to 11. So again, we have just decomposed this part. Here we have nothing to do. It's already in good form. So now we need to evaluate inverse Laplace transform of each fraction here, right? Okay. So let's start with the first one. The first one is inverse Laplace transform of 2 over s minus 3, right? What is it? I can just write it as, take this 2 out, inverse Laplace transform of 1 over s minus 3, right? Which is equal to 2 times, what do we have here? Actually, we know that actually is e to the power 3t. Anyway, I'm just trying to use that formula here. We have inverse Laplace transform of 1 over s, where s should be replaced by s minus 3, right? And what functions Laplace transform is 1 over s? We know that is equal to 1. And because of this s minus 3, that's equal to 2 times e to the power 3t, right? S minus a, here we have e to the power 8t. Okay, with the first part, we are done. How about the second thing? Inverse Laplace transform of 11 over s minus 3 squared. Okay, equals, again, it's just a constant number. And now I can write it as inverse Laplace transform of 1 over s squared, where s should be replaced by s minus 3. Okay, we don't need this line here. Equals 11 times. Now that is our capital F of s, right? So we know that what functions Laplace transform is 1 over s squared. That is just t. And how about this thing? This thing gives us e to the power 3t times this function gives us t, right? In a similar way, how about here? Inverse Laplace transform of 2 over s minus 3 to the power 5. And for this, I am going to use that thing. What is it? Laplace transform of t to the power n is equal to n factorial over s to the power n plus 1, right? Just keeping this in mind, this thing is equal to first 2 is a constant, Laplace, inverse Laplace transform of 1 over s minus 3 to the power 5. That is s to the power 5, where s should be replaced by s minus 3. Right? So what I need here to be able to write in this form. So here 4 factorial is missing, right? So if I just multiply here by 4 factorial times 4 factorial, right? Nothing changed. Okay, that's just, it looks like 1. It should be 4 factorial, right? And now because of this thing, here we have 2, 4 factorial is, what is 2 over 4 factorial? It is 2 over 4 times 3, 12. 12 times 3 is 24. That's equal to 1 over 12. So here we have 1 over 12 times because of this e to the power 3 t, right? And here we have the f of s, that is, what is it? T to the power 4. Okay, so that's just notes. We don't need them. So now we can write our final answer, dots, dot, dots. So inverse Laplace transform of the given function is, what is it? The first part is 2 to the power 2 times e to the power 3t, right? Plus 11 times e to the power 3t, and here we have t. Actually, I need to write t here. Plus what we have here, 1 over 12 times e to the power 3t and t to the power 4. Okay. Now let's see one more example. After that, you may have break. Okay. Another example, an initial value problem. How do you solve this problem using Laplace transform? Now, procedure is the same. Question is a little bit different. Initial condition is a bit different, but the idea, the technique, the method we are going to use is exactly the same. The first step is we have to take Laplace transform of both sides, right? And after that, by using the linearity property of Laplace transform, I can write it as Laplace of y double prime plus 4 times Laplace of y prime plus 6 times Laplace of this. And on the right hand side, and also I can just separate them, Laplace of 1 plus Laplace of e to the power negative t. So now we know how to evaluate this thing, right? Y double prime, that is s squared times capital Y of s minus s times y of 0 minus here s is decreasing the degree of actually the order of y. It is increasing. So here we have s times y of 0 minus y prime of 0. Plus here we have 4 times, how about Laplace of y prime, s times capital Y of s minus y of 0. Plus here we have 6 times y of s. And what is the Laplace transform of 1? It's just equal to 1 over s. And how about e to the power minus c? A is negative 1, 1 over s minus a, right? That is my s minus 1, it is s plus 1. Okay. Next step is, it's just what we got here is an algebraic equation in capital Y of s. So I'll try to make this capital Y of s the subject of this formula. So we have to isolate this and leave it alone on the left hand side, take everything else on the right hand side. So, and also by using these initial conditions, y of 0 equals 0, so this will disappear, y prime of 0 equals 0, and also this will disappear, and also this will disappear. What we have here is s squared, right? And this is 0, and that's 0. Here we have 4 times s, 4s, right? And here we have 6, here we have 6, y of s. On the right hand side, bring into a common denominator, s plus 1 plus s, that is 2s plus 1. In the new denominator, s times s plus 1. Now, if I just do it both sides by this expression, what we got here is capital Y of s equals this thing, right? I don't do anything, we just divided both sides by this expression. And also, as you see here, I cannot factorize this, right? So that is, we cannot factorize this thing, but I can write this fraction again as, here we have the first factor, the second factor, the third factor, right? A over s plus b over s plus 1, plus because of this is quadratic, I need to have here linear, right? The degree is 1 less than this. Anyway, here we have c times s plus d, right? And you know the rest, what we do here, bring into the common denominator, 2s plus 1 on the left-hand side, on the right-hand side, a times this plus this times this, that's what we have here. B times s squared plus 4s plus 6, plus now cs plus d times s plus 1, s times s plus 1. Now substituting some suitable values for s, we can determine the values of a, b, and c, right? For example, let's say s equals here negative 1, or not negative 1, let's say s equals 0. If s equals 0, because of here, right, this will disappear, and when it is 0, it is 6, when it is 0, 1. So a equals 1 over 6, right? Now, how about if s equals -1? If s equals -1, this will disappear, and this will disappear. Only this thing is left. It is 1 minus 4 minus 3 plus 6 is 3, right? And evaluate this, I get b equals 1 over 3. All right. And after that, substitute some other suitable values, maybe 0 or 1, whatever it is. I can evaluate c and d. Okay, these things are, you know how to do that. That's why I'm not showing every step here. Now, if you substitute here into this expression, right? I know a, that is 1 over 6 here. B, it is 1 over 3. It is here. And c, that is equal to -1 over 2. D is also negative. That's why I write here negative minus 1 over 2. S plus 5 over 3. Okay. And also, actually, we are familiar with this fraction expression, right? Quadratic expression. We can just write it as s plus 2 squared plus 2, right? And also here, since I have s plus 2, I try to have s plus 2 in the numerator. Just doing simple manipulation, algebraic manipulation, I can get this thing. Okay. Here we have the first thing, 1 over 6 is constant. Take this out, 1 over s, right? And 1 over 3 is a constant also, 1 over s plus 1. And here, 1 over 2, take this out, s plus 2, right? And also, if you remember, this one is 5 over 3. I can write it as, what is it? 1 plus 2 over 3, right? 1 plus 2 over 3. That's why here we have 2 over 3. And I multiplied it by negative square root of 2, square root of 2. And the things are actually, you're familiar with the rest, right? So we can just write here our y. Y of x is equal to, the first one is 1 over 6, right? And what function's Laplace is 1 over s? It is just 1, right? Plus, second one is 1 over 3 times, and also you're familiar with this. What is it? It is e to the power minus t, right? Minus 1 over 2 times. Here we have s plus 2 squared plus 2s plus 2. And if I just change this with capital S, capital S, capital S squared plus square root of 2 squared. So what is it? It is e to the power minus 2t, right? Because our a is here, just 2, minus 2 actually. And here we have, what is it? Because this one is s, right? That is cosine of square root of 2t. Minus, how about here? 2 over 3 square root of 2 times. Here we have k s squared plus k squared. So here we have e to the power minus 2t times sine of square root of 2t. Okay, that is the solution of the given initial value problem. I mean, using that Laplace transform, this is how we solve the second order linear differential equations with constant coefficients. Okay, guys, now it's a break time. Let's have break for 10 minutes. After that, we'll continue.